Most chemical reactions take place in solution because this allows the best contact between reacting species. A solution is another term for a homogeneous mixture, a mixture that looks to have uniform composition and properties throughout its entire volume. We separate a solution into its individual components: the solvent, the dissolving medium. Most often in Gen Chem, the solvent is water, and the solute, the stuff that's dissolved in the solution. The relative amount of a solute component in a solution is known as its concentration. The most common concentration unit in chemistry is molarity. That's because it's very convenient. Molarity multiplied by volume is going to give you moles of your solute. This is true provided that your volume is expressed in liters. Essentially what we have is units of moles per liter, which is our molarity, times liters, and that's going to give us moles because units of liters cancel out. Let's work through a relatively easy problem. How many grams of solute are contained in a solution of this volume and this concentration, and we're given the formula weight. So what we can do is multiply molarity times volume to give us moles of solute, and then using the formula weight we can quickly calculate grams. I've started this problem the way I suggest you always start with problems in molarity. Translate molarity to moles per liter. Do not keep the unit uppercase M. That's going to lead to confusion. Use moles per liter. We multiply by 1.75 liters to get 2 moles of our solute. Now we simply multiply by the formula weight to yield grams of solute. And we get our calculator answer. We go back and look at sig figs. 3 sig figs, 3 sig figs, 5 sig figs. So our least number of sig figs is 3. That's what we're limited to. And our final answer is 114 grams of solute. The table here is primarily to remind you absolutely must memorize the names and formulas for the following polyatomic ions. Those that are most common are in bold. So focus on those first. Salts are another name for ionic compounds. We can recognize an ionic compound because it has a metal plus a nonmetal, or a metal plus a polyatomic ion, or a combination of polyatomic ions. Salts can either be insoluble or soluble. We'll first consider the soluble salts. When soluble salts dissolve, they dissociate into ions. They exist as separated or dissociated ions in aqueous solution. Insoluble salts do not dissolve in water, nor do they dissociate into separate ions. Instead, they exist as a solid or a precipitate in water, meaning that their ions remain locked in place in their ionic solid. So soluble salts dissolve and dissociate into ions. Insoluble salts do neither. So let's practice identifying the number and type of ions that are in solution for the following dissociation reactions. Remember that polyatomic ions tend to stay together in dissociation reactions. Let's look at this first compound. If we put this in water, it's going to dissolve, it's soluble, and it's going to dissociate into ions. We know that we're going to get bromide ions from the bromine. And further, we know that there's going to be 2 bromide ions because of the 2 subscript here. Copper, we can determine the charge as being 2+ because we know the charge on the copper has to be equal and opposite to the charge on the 2 bromide ions because the compound itself is electrically neutral. For this next compound, we recognize that we have a perchlorate ion. In fact, we have 2 perchlorate ions, Cl04 minus. If we forget the charge on the perchlorate ion, this problem is a little bit forgiving because calcium is a 2A metal. We know the charge on the calcium ion is going to be 2 plus. Therefore, since we have two perchlorates, the charge on each has to be minus 1. For potassium phosphate, another polyatomic ion we recognize, the phosphate ion, and we're also going to have 3 potassium ions. Potassium is 1 plus because it's a 1A metal. We also know that the 3 potassiums have to counteract the net minus 3 from the phosphate. We have 2 different polyatomic ions in this next compound. When this dissolves, we're going to get ammonium ions, NH4 plus, and we're also going to get sulfate ions, SO4 2 minus. And further, we know because of this subscript 2 that we're going to get 2 ammonium ions. Sodium carbonate is soluble when it dissolves. We're going to get a carbonate ion. That's our polyatomic ion we recognize. And we also know that there's going to be 2 sodium plus ions. Potassium dichromate. Okay, the dichromate ion is not as common as some of the other polyatomic ions, but we can still recognize it. It's Cr2O7 and the charge is a minus 2. If we happen to have forgotten what the charge is here, we can look at the fact that there's 2 potassium ions, and we know that each potassium ion has to be a plus 1. Iron 3 nitrate, another compound with a polyatomic ion. In this case, we have 3 nitrate ions. So it has a net minus 3, so we know the charge on the iron ion has to be a plus 3. The final compound is magnesium hydroxide. We're going to get magnesium 2 plus ions. Magnesium's a 2A metal. It's going to form a 2 plus charge. And we're also going to get 2 hydroxide ions. Okay, note you can write hydroxide ions either as HO minus, as I've done here, or equivalently, you can write this as OH minus. It's the same. I prefer to use HO minus because this negative charge is actually associated with the oxygen, not with the hydrogen. For doing stoichiometry problems in solution, we need to keep track of the concentration of ions in solution. So we're going to practice calculating the concentration of ions in the following solutions. First off, 0.250 molar KBr. Let's remind ourselves of the dissociation reaction. KBr will dissolve in water. When it does, it will dissociate into a K plus ion and a Br minus ion. In solution stoichiometry problems, it's a very good strategy to translate molarity, uppercase M, as moles per liter. For example, 0.250 molar KBr is 0.250 moles of KBr per liter. This allows us to easily set up the mole-to-mole conversion factor to convert between one chemical and another. So we've set up our mole-to-mole conversion factor. This is a 1:1:1 mole ratio, so this is an easy practice problem. And what we see is that as we've set this up, we now have units of moles of potassium ion per liter of solution, which is the concentration of potassium in moles per liter. I'm going to introduce a notation here of square brackets. If you have something inside of square brackets, it's the concentration of that entity in molarity. So 0.250 moles of K plus per liter can be rewritten as K plus is equal to 0.250. So that's potassium ion concentration is 0.250 moles per liter. Let's do the same for the other ion. We start with 0.250 moles of our solute, KBr, per liter. In this case, every mole of KBr is going to release a mole of Br minus ions. So again, we get the concentration of 0.250 moles per liter. In this case, it's moles of Br minus per liter. And we could rewrite this if we wanted as the concentration of Br minus is equal to 0.250. For aluminum chloride, we first start with a dissociation reaction. Aluminum chloride, soluble, when it dissolves, we're going to get Al3 plus and 3. Let's look at our mole to mole ratio. Every mole of aluminum chloride, when it dissolves, is going to release a mole of aluminum 3 plus ions. If we look at our units, we see moles of aluminum chloride cancel out. We have moles of aluminum 3 plus ion per liter, which is what we want. And our concentration of aluminum 3 plus ion in solution is 0.120 moles per liter. For the chloride ion, we again start with the concentration of our solute. Our mole ratio is that every mole of aluminum chloride is going to release 3 moles of chloride ion. So we do the math, 0.120 times 3, and that gives us 0.360 moles per liter. Okay, our last problem here, sodium sulfate. When it dissolves, it'll dissociate into ions, giving you 2 sodium ions and a single sulfate ion. We translate molarity to moles of sodium sulfate per liter, and our mole ratio is a 2-to-1 mole ratio. Every mole of sodium sulfate releases 2 moles of sodium ions. So the concentration of sodium ions is twice that of the sodium sulfate. And for the sulfate ion, we see every mole of the sodium sulfate is going to release a mole of sulfate ions, so the concentration is exactly the same, 0.2 moles per liter.